So first up is the inverse transforms worksheet. Okay, so moving on. So what I decided to do, and this is purely because I forgot, is I'm just going to do it as I've been doing it all semester. There'll be a worksheet for this stuff and a worksheet for the next stuff, and I'll just put the review worksheet online with the solutions for you to go through. This is also pretty important, so I kind of don't want to rush through it. Because what we're doing now is using the Laplace transform to solve initial value problems. Okay. Two things we're doing today. We're going to do the solutions of initial value problems, where all the Laplace transforms and inverse transforms are basic. Then we'll look at convolution. What is convolution? And that will allow us to solve what are known as Volterra integral equations. Next class, we will look at piecewise forcing functions. That involves the unit step function and the second shifting theorem. These two theorems are really important. It tells you how to transform the derivative of a function, second derivative of a function, and by the way, well, yes, it only shows up the second derivative. This can naturally extend to any order derivative. Right. So, for instance, if you transform the third derivative in the s cubed transform of f minus s squared f double prime, right? No, minus s squared f of 0 minus s f prime of 0 minus f of 0. S cubed transform of f minus s squared f of 0 minus s f prime of 0 minus f double prime of 0. That's what it is. Right, so you always start with the f of 0 and then work your way down from there based on the order of the derivative. I don't think we have to worry about that because I think everything will work with it for second orders. Convolution. Convolution of two functions, f and g, is defined as the integral from 0 to t, f of tau times g of t minus tau d tau. By the way, it can also be proven that you can flip that. So the convolution is commutative. You could also do g of tau times f of t minus tau, integral from 0 to t. Convolution theorem states that if you take the Laplace transform of the convolution of two functions, it is the product of their Laplace transforms. So, real simple. Why is this not working? Oh, that's why. Okay, perhaps. Right, an integral of that form is a convolution integral. Right, then obviously the convolution theorem provides a way to evaluate convolution integrals. Also, any equation of this form, 8.6.11, is called a Volterra integral equation. And obviously convolution theorem will allow us to solve that. So the idea behind solving initial value problems using Laplace transforms is we just take the Laplace transform on both sides of the equation. Right, then use your linearity property, and now use the results. Laplace transform of y double prime s squared times the Laplace transform of y, which we will write as capital Y of s, minus s times y of 0 minus y prime of 0. That was just for y double prime. Now the Laplace transform of y prime would be s times y of s minus y of 0 why did I write 5 there? That should have been 6. And then 5, the Laplace transform of y is just capital Y of s. What is the Laplace transform of e to the 2t?
One over s minus 2.
Solve for big Y. So y of 0 was 2, that becomes 2s, y prime of 0 is 3. That should have been minus 6. Oh dear. I'm in weekend mode already. goes through x minus 6s minus capital Y minus 2s minus 3 plus 12 is plus 9. So this is where we're at right now. Right, so obviously we're just going to divide both sides by the s squared minus 6s plus 5. But I'm going to write it in a specific way. It'll be 3 over s minus 2 times what we were dividing by. And then plus the 2s minus 9 divided by that. Instead of trying to write it as one single fraction, I'm going to keep it as 2. That is what big Y equals. But big Y was the Laplace transform of little y, right? So now you take the inverse Laplace transform on both sides. And now we use the techniques that we were working on last time. What is the Wolfram command to do partial fraction decomposition? We have two fractions, right? We're going to do each one individually. First one. Take them to the right screen, that would be nice. There we go. 3 over s minus 2 times s squared minus 6s plus 5. And then 2s minus 9 over that. Oh, that's nice. Since they're being added, let's just go ahead and add them. There's a reason I didn't put them together. Because it could have been possible that that second fraction didn't decompose. So I just wanted to be safe. So I'll just simplify their sum. Oh, that is so nice. It looked hideous, but now look how sexy it looks.
On the calculator, it would be the expand command, right?
Yeah. And remember, the inverse transform is also linear. What is that first transform?
Would have to be unitwise too.
What's the second transform?
Minus e to the 2 too.
And what about that final one?
Plus 5 times e to the 2.
Is your solution? This is actually way more efficient in terms of coding than the technique that we used. How many weeks ago was it now? That if I would have used undetermined coefficients on, so whenever we covered that. In terms of coding, this is way more efficient. Also, by doing it by hand, it's also more efficient, isn't it? Because now you don't have to worry about finding your complementary function, which is easy anyway. Then finding your particular, and then applying your initial conditions after all that. To find your C1 and C2. Laplace transform does it all together. However, Laplace transform can only be used on initial value problems. It cannot be used to find a general solution. So your challenge is to go back and solve this using the techniques prior and verify you get the exact same thing with more algebra. Again, we're going to use Laplace transforms. I am now going to be skipping a lot of the intermediate steps. What is that Laplace transform? E to the 8e to the negative 2t.
S minus 2. Or S plus 2.
Right, s minus negative 2. Okay, so we're going to have plus 8s minus 4 plus 12 is plus 8. Since that's where we're at right now, I think I'm going to go ahead and just do the partial fraction decomposition right now.
Is that minus or plus?
That's a minus.
Now it looks better.
Just put that up there. That's the output from Wolfram. Y of t then. Plus 1. This plus 2 and then right, of those inverse transforms. What's the first one?
E times E.
Negative 8. Negative 8. I agree, it should be e to something. Negative t. Remember, it's s minus something. What's the second transform?
Eight thirds e to the negative 2t.
What is the third transform?
Eight six e to the negative a half t.
You are correct, but I don't like the answer.
4/3.
4/3. Well, you have to factor out that 2 from the denominator. So write it as s plus a half. There's your solution. Okay. And so s squared y of s minus s y of 0 minus y prime of 0 plus 2 times s big Y of s minus y of 0 plus 2 times big Y is the Laplace transform of 1 and what is the Laplace transform of 1? Oh, at this point, yeah, well, I'm going to do this as well. So this is the table that's going to be provided with the exam. I'm going to upload it right now. Right, so you don't have to actually memorize any of the transforms. They're all going to be given there, along with some of the basic inverses.
What is the factorial? What does that mean? Like n factorial?
You don't know what factorial is?
For some reason it's confusing.
5 factorial. 5 times 4 times 3 times 2 times 1.
Wow.
That's what factorial means.
Okay.
Right, so it's whatever the power is. Factorial just means it's the product of that with all of the integers less than and up to 1. Or down to 1. Right, so 10 factorial would be 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Which, by the way, is a very large number.
So like Laplace t to the 9 would be like.
Yeah, the transform of t to the 9th would be 9 factorial over s to the 10th.
Okay. And then we just plug that into the calculator.
9 factorial is, again, a pretty large number.
Okay.
10 factorial, if I remember correctly, is like 10 million, I think. It's either a million something or 10 million something. It's pretty large. Okay, should now be available in SharePoint. The transform of 1 is just 1 over s, right? So we should find that big Y is just one over s times s squared plus 2s plus 2 minus 3s plus 5 over s squared plus 2s plus 2. Again, let's just go ahead and do the decomposition on that right now. There's what it's going to give us. Oh, that one's not bad. 1/2 over s. I can live with that. Unfortunately, that second one is a bit of a problem. So I think here's how I'm going to write it to start. Right, it's 1/2 times a fraction. Now we're going to have to complete the square on that, aren't we? Should just be what, s plus 1 quantity squared plus 1. And then write 12 as 7 plus 5. Maybe I'll write the 1/2 over s the same way, it's just 1/2 times. Like that. This is what y of t would be then. What's the inverse transform of 1 over s?
1.
What is the inverse transform of s plus 1 over s plus 1 squared plus 1?
Seven pounds. E to the negative t cosine t.
And that last one is just e to the negative t sine t. Times the negative 5/2. There's your solution. Just for fun, what's the particular solution? One half. Which means your complementary would have been c1 e to the negative t cosine t plus c2 e to the negative t sine t. Use that. What were the roots of the auxiliary equation then? Keep going.
Minus 1 and I.
Not minus 1 and I.
What's the minus?
Negative 1 plus or minus I. Alright, good. Let's move on to convolutions. We're given f of t is e to the at, g of t is e to the bt, where a and b are not equal. They want us to verify the convolution theorem. Right, so verify that the transform of the convolution of f with g is the transform of f times the transform of g. Let's start simple and just calculate these transforms, these basic transforms. What's that transform?
1 over s minus I.
What is that transform?
1 over s minus b.
It's 1 over s minus a times s minus b. Right, or that, I don't know how the integral is going to work out. So let's call that 1. Now, we have to find the convolution. That's the integral from 0 to t. F of tau times g of t minus tau d tau.
What does tau represent?
It's what we're integrating with respect to. Do that. Right? So we're going to have bt plus a minus b tau, right? But with respect to tau, isn't e to the bt constant? Right, so I'll just show this intermediate step. So we can factor out that e to the bt and be left with this. What is that antiderivative? Isn't that just which when you evaluate gives this. Now I have to simplify that, right? Well, when you multiply, you just add exponents. So isn't that just going to be e to the at over a minus b? And what, minus? That would be our transform now, right? That's what we're taking the transform of, which we can write as not inverse. And what's the transform of e to the at? And transform of e to the bt? Simplify 1 over s minus a minus 1 over s minus b. What do you get?
Negative a minus b, or a minus b.
A minus b, what?
Over s minus a times s plus b.
A minus, s minus a times what?
S minus b.
Isn't that just 1 over s minus a times s minus b? Call that 2. What was 1? Turns out I don't need this. So I'm going to go ahead and erase that. Isn't it the same? You're working really hard today. I don't know why. So we verified convolution theorem for those two functions. I want to know what's going on here. Why the hell is that memory at 80% use? How is this module installed? Okay, now memory's dropping. Okay, something's going on. No idea. I know you're working way too hard right now. I want to skip down to here for right now. Solve a Volterra integral equation first, and then go back and look at the other three. So take the Laplace transform. Actually, before I do that, let me rewrite this. Because isn't this a convolution? Specifically, it's the convolution of y of t with e to the negative 2t, isn't it? Now take the Laplace transform. We get big Y of s, Laplace transform of 1 plus 2, Laplace transform of y of t convoluted with e to the negative 2t. What's the transform of 1? Transform of a convolution. Convolution theorem says, isn't that the product of the transforms? So what's the transform of y of t? That's just big Y, isn't it? Times, what's the transform of e to the negative 2t?
Over s plus 2.
We can make that look nicer. Move the y of s over to the other side. Let's write that as a single fraction. Simplify. 1 minus 2 over s plus 2. What is it?
S over s plus 2.
Yeah, that's right. S plus 2 over s squared, can that be simplified? I don't want to say simplified, because that technically is simplified. Can that be expanded very easily? What does it expand to?
Used to be s over 2, s plus 2 over s times s plus 2 over s.
It's probably not smart to do that when you're right in front. Ten points off your final grade just for that.
One
You
over,
try to not take those.
1 over s plus 2 over s squared.
Makes me sad that you need your calculator for that.
Sorry.
Just a single denominator, isn't it? It's a monomial. So isn't that just simply s over s squared plus 2 over s squared? And then simplify from there. Now, it's been a while since algebra. Oh, look how easy that is to solve. Because remember, big Y is the Laplace transform of Y of t. So just take the inverse transform. What's the inverse transform of 1 over s? That one's easy. What's the inverse transform of 2 over s squared?
15.
It's 2t. There's your solution. Y plus 2, sorry, 1 plus 2t. Now we can solve Volterra integral equations. And don't ask me where they come up because I don't remember ever seeing it in physics. So if it has an application, I have no idea.
I'm guessing.
Oh, I have no idea. I would assume so. But maybe not. Because Gauss wasn't technically in mathematician. That's arguable. The dude invented calculus just to describe physics. Actually, the dude invented an entire branch of calculus on a dare. He was dared to explain the orbits. And then he invented, what was it, integral calculus, I think, to explain that. Of course, he also thought that colors were pressure on the eye, so he stuck his eye with a needle to test them. He also drank mercury for science. So he also argued maybe he wasn't that intelligent. So here they want a formula for the IVP. Notice that we can't actually directly solve it. The best we can do is come up with a formula. We're going to start the same way. Laplace transform. We're just going to call the Laplace transform of f of t big F for simplicity. I'm going to have what? Minus k naught of s plus 2k naught minus k1 So big Y would be big F of S over S squared minus 2S plus 1. Then we're going to have plus K naught S plus K1 minus 2K naught all over same thing, S squared minus 2S plus 1. Oh. But isn't S squared minus 2S plus 1 S minus 1 squared? We need to do it. Yeah, we need to do partial fraction decomposition on that. Second one. Bummer. Let me just see if we can do it. Should be able to. Let's see if that works. 0 times S minus Q1 minus 0. It does. That is so easy. That's what it gives. Your calculator should be able to do the same thing. Just be careful. I have to explicitly define multiplication. Because if I just write this as K0S, it'll read that as a single string. So it'll read as a single variable and not a product of variables. Your calculator is the same way. So you have to write K0 then times S. And that's true whenever you're using product of multiple variables. Just always separating with multiplication so it doesn't read as a single variable. With that, that will allow us to write y of s as big F of s over s minus 1 squared plus k naught over s minus 1 plus K1 minus K naught over S minus 1 squared. Y of t is then the inverse transform. I'm going to write it this way. F of s times 1 over s minus 1 squared plus the inverse transform of k naught over s minus 1 plus the inverse transform k1 minus k naught all over s minus 1 squared. Start with that middle one. What is that transform?
K not e to the t.
What about the second?
K1 minus K naught all times e to the t.
Now I have to deal with that first one. Oh, but that is the transform of f of t, right? What's this the transform of? So we're taking the inverse transform of a product of transforms. That's convolution. Right, so again, the convolution theorem has technically two parts, the transform and then its inverse transform. I'm going to factor out e to the t. And then use the definition of convolution. There's your formula for the solution. The other two problems are identical, it's just the left-hand side is a bit different. But the way you go about it is exactly the same. Questions on convolution or solving initial value problems?
So when do you use the definition of convolution?
When you actually have to calculate convolution.
So when there's a function multiplied by.
If you're taking the inverse transform of the product of functions, that is convolution. That's if it was, for instance, the inverse transform of 1 over s times 1 over s minus 2. You know what the inverse transform of 1 over s is. You know what the inverse transform of 1 over s minus 2 is. It's the convolution of those two. I'll show this real quick. I did update the due dates. So both the quiz, which I didn't change the posting, so that should post today after class, and the final group project will be due on the 14th before the exam. And we only have one more class meeting after this, before the exam. Oh, I forgot to do meeting time, whatever. So it's gonna be at the end of class, so I won't bother with it. Your best bet. Oh, actually, I'll see you Monday. Thank you for making on Monday. And I can break this one. Oh, wait, never mind. No, it's also,
I could just stay on the,
no, I'm leaving right out. I have to leave right after the
I
pickup.
usually keep it early.
If you want to come in. Yeah, or maybe just,
I usually take it like, I'll start at 11 and then take it